all of you. Welcome to the 38th lecture on the course on analysis and modeling in chemical engineering. In this week, we have been discussing graph theory. We discussed some definitions on graphs. First, we discussed like acyclic graphs, where we discussed the idea of reachability matrix, Boolean sum, and so on. And then we also discussed the idea of cyclical nets in the previous class. And finally, the idea of maximal cyclical nets. So, in this lecture, I will go further and discuss two other ideas. That's the idea of incidence matrix and augmented incidence matrix. And then I will tell you how we can write balance equation, let's say material balance equations using graphs, right? And finally, we'll take some examples, and then in the following classes, we will discuss more detailed applications of graph theory. So, we'll define one other matrix that's called incidence matrix for a graph that contains the information also about the edges in the graph apart from only the vertices, right? So, Boolean matrix tells me whether there is a connection between one vertex to the other, but it does not contain information specifically or explicitly about the edges, right? So, how do we do that? So, let's say I have a simple graph 1 to 2. So, in this case, the Boolean matrix looked like this, is labels 1 2 from and 2 1 2, and there is a flow from 1 to 2. So, I put 1 there and every other term is equal to 0. That is my matrix, the Boolean matrix. But now I will define one other matrix, that's my M matrix, that is going to contain information regarding this edge as well, right? So, let me call this edge as some E1. So, now what I will do, I will put the vertices along the rows and edges along the columns, right? So, we have only one edge here. So, we have a matrix that looks like this. And now, what I will do is I will put a -1 here if it is leaving a particular vertex and +1 there if it is reaching a particular vertex. So, let us say E1 is starting from 1. So, it is leaving 1. So, in the first row I will put a -1 and it is reaching 2. So, it is basically the incoming at 2. So, I am going to put a +1 there. So, this particular matrix is what I call the incidence matrix. In fact, now we can also include the effect of interfaces in the system, right? So, you can imagine in this particular simple graph, one must be getting flow from somewhere. So, let me define an input interface as 1, and similarly 2 must be sending things somewhere, right? So, let me define an output interface there. So, let me call this E1 edge as we originally had, but let me define one more edge E0 here and E2 here. So, in that case, if I want to include those edges, interface edges in our matrix, what I will define is my augmented incidence matrix that will look like this. So, we again have the vertices 1 and 2, but the edges are now going to contain, of course, the earlier internal edge E1, but also E0 and E2, and you can see that the matrix is no longer a square, right? Even the earlier matrix was not a square, it was always rectangular, right? That is, the number of rows is equal to the number of vertices and the number of columns is equal to the number of edges, right, in both these matrices. So, for E1 we still have the same story, -1 and +1, and E0 is incoming at 1. So, therefore, I put a +1 there, and E0 is not connected to 2. So, therefore, I put a 0 there. So, -1 if it is outgoing, +1 if it is incoming, 0 if not connected, right. Similarly, for E2, E2 is not connected to 1, but E2 is outgoing from 2. So, I put -1. So this matrix that is now containing two additional columns from the incidence matrix is what is known as the augmented matrix, right? Now you can see like what is the advantage of this. So let us say, for example, I wanted to write the overall material balance on a flow sheet, simple flow sheet like this. So now I can imagine that this as represents kind of the flows, right? And let me say this E naught, E1, E2 indeed represents the flow. So I can now have a vector E that is E naught, E1, E2 that represents my flow. And now if I do this A dotted with E, what I am going to get is the following. So we have -1, +1, 0, +1, 0, -1, and that dotted with E naught, E1, E2, and this gives me something like the first row will give me minus E naught plus E1, and the second one will give me sorry, it is, yeah, it has to be E1, E naught, E2. So this A dot E is going to look like minus E1 plus E naught, and the second row will give me E1 minus E2, which in fact are the balance equation for this flow sheet. So if I set it equal to 0, 0, what I should get is minus E1 plus E naught is equal to 0. That is the balance equation for the first vertex, and the second row will give me E1 minus E2 is equal to 0. That is the balance equation for the second vertex, right? So basically, I can use the augmented incidence matrix to write the balance equation for this. The only difference is the augmented matrix include the effect of the system interface, right? The incidence matrix does not include that particular information. Okay, so let's take one more example, slightly more complicated graph, and try to do the incidence matrix for this particular graph, right? So let me label the vertices by something. So this becomes my, let's say, E1, this is, let's say, E2, and this is, let's say, E3, and I call this one E4, this one E5, this one E6, this one E7, and then again I will have the vertices along the rows. So I will label like this: vertices 1, 2, 3, 4, 5, and I will have the edges along the column, and we have 7 edges: E1, E2, E3, E4, E5, E6, E7, and what comes here is my incidence matrix. Let me draw some lines to guide. Just to make it easier to differentiate, I am drawing these lines, it's not required. So we have something like this, and now we just simply see for every edge, I will see along the columns. For every edge, I will see whether it is incoming or outgoing at a particular vertex, right? So E1 is outgoing from 1, so it is -1, and E1 is incoming at 2, so I put a +1. E2 is outgoing from 1, so it is -1, and E2 is incoming at 3, so I put a +1. E3 is outgoing from 1 again and incoming at 5. E4 is outgoing from 2 and incoming at 3, and E5 is incoming at 3 and outgoing incoming at 2 and outgoing from 3, and E6 similarly is coming from 3 going to 4, and E7 is coming from 4 going to 3. You can see if I add all the columns here in the incidence matrix, they are all summing to 0 because every vertex is coming from somewhere and going from somewhere. The same is not true for the augmented incidence matrix because you also have interfaces. But for incidence matrix M, if I sum up all the rows, all the columns, we are going to basically get zeros, right? So we get, let's say, 0 here. All right. Let me now do the augmented incidence matrix for the same case. So now we will have additional columns in the matrix. So let me say that these columns are whatever remains, I will simply put the additional columns, whatever comes there, right? So let me now have additional edges, E7. I think E7 we had, so let's start from E8 and E9, and let's say E10, right? So now what are the additional columns we will have? They are going to be E8, E9, E10. So we will have again the vertices 1, 2, 3, 4, 5, and we will have the edges. So E1 to E7 will remain my unchanged. This is my augmented matrix M, and then I have E8, E9, E10. Let me draw these lines just to help. And then for E8, it is coming at 1, so there should be plus 1 here. E9 is going from 4, so there should be a minus 1 here, and E10 is going from 5, so I put a minus 1 there. So it has all the M matrix plus the additional columns, whatever I have indicated in there. Okay. I have already said that we can write the balance equation using the augmented incidence matrix, but let me put the balance equations for this particular case. So we have A dot E is equal to 0, and E in this case is basically we have defined from E1 until E10. So E1 to E10. So A dot E, let us see what does it give me. So it will give me basically 5 rows, right? And for the first row, let's say, if I do this, we'll have minus E1, minus E2, minus E3, and then plus E8. So we get minus E1, minus E2, minus E3, plus E8. So by the way I have defined E1, E2, E3, E4, E5, E6, and E7. And then for the second row, I am having plus E1 minus E4 plus E5 plus E1 minus E4 and then plus E1 minus E4 plus E5. Let me again also label the edges here. So we have E8, E9, E10, E1, E2, E3, E4, E5, E6, and E7. And then there is no interface at 2, right? And then for third one, we have E2 plus E4 minus E5 minus E6, E2 plus E4 minus E5 minus E6, and then plus E7. And then finally, for fourth one, we have E6 minus E7, but we also have one element here, So E6 minus E7 minus E9. And for last one, we have E3, and then in augmented matrix, we have minus 1 here, E10. So E3 minus E10, and that set equal to 0 pretty much gives me the balance equation for this case, right? Let us look at the vertex 1. So we have E1, E2, E3 are all the leaving streams output. So minus E1, minus E2, minus E3 is the minus of output, and E8 is coming. So if I sum these two, I get 0 at a steady state, of course. And then for vertex 2, E1 is coming and E5 is coming from 3. So E1 plus E5 becomes input. E4 is the only output. For vertex 3, it has multiple inputs. E2 that comes from 1, E4 that comes from 2, and E7 that comes from 4, and E5 and E6 are the output. It becomes 0. For vertex 4, we have E6 as the input and E7 and E9 as the output. And for vertex 5, E3 is the only input and E10 is the only output, right? So we have a neat way to write the overall material balance equation at a steady state using the augmented incidence matrix, and therefore this graph can actually represent the balance equations very nicely. So let's take some examples, right? So now I am not giving the graph, I am giving you the R matrix, and I want to write the incidence matrix for this graph, right? The very first step, what I will do, I will first draw the graph, and once I have drawn the graph, then I can write the incidence matrix. That's always intuitive to do because we can see what is happening in the graph and then write the incidence matrix. So let me first label the vertices. So it is going from will come here and 2 will come here. So there are 6 vertices. That's why we have a 6 by 6 matrix. And let me first put the 6 vertices here. 1, 2. I don't know how they are connected, but I know that there are 6. And now we can look at the R matrix and see from 1, one can go to 2, 4, and 5. So from 1, I will draw lines to 2, 4, and 5. And then from 2, I can draw line to 1, then 3, and also 4. And from 3, I can do a line to 4. From 4, I can do to 2 and 4. So I need to come back, right? And for 4, there is also coming to 4. Until so far, we have not encountered this kind of a thing, but we are having some kind of a self loop of 4 coming back to 4. And then from 5, we can go to 6, that is right here. And from 6, we are going back to 1. Now, in order to do the incidence matrix for this case, we need to label all the edges in the graph, right? So, I can do it like E1, E2, E3 and so on, right? And I will have something like, let's say, E1, E2, E3, E4, right? I can label all the edges, and then I can put the vertices along the rows 1, 2, 3, 4, 5, 6, and I will have all the edges along the columns, and whatever rules I have followed to write the incidence matrix, I am going to write. Now, we will have a small problem for 4, this self loop, because it is both incoming and outgoing, right? So, therefore, the question is whether to put -1 or +1. The best idea is that we will ignore this self loop because there is a confusion whether to consider it or not. right? In fact, from the process perspective, there is always a self loop. The system always affects itself in some way, right? So we are going to ignore this particular self loop in the graph, right? And we will see later when we discuss about like equation solving using graph theory, that what exactly self loop amounts to and things like that. Okay, so we'll ignore the self loops and we can do pretty much the same procedure in there, right? By the way, there is also a line from uh, 2 to 6 which I have missed here, a line from 2 to 6 because that is appearing in the Boolean matrix. Let us do one more example. So we have R given and we need to find the reachability matrix for this graph, and then using that we want to identify the cyclical net in the graph if we have any. So we have that is given. Let me try to find R square. For doing that, we need to basically multiply the rows R with R itself. So we'll see which element of a particular row is 1, and then look at the corresponding column in there, right? So let me do it for the first row. Third and sixth element is 1. So I am going to locate columns where third and sixth element is 1, and that is true for the last column right here, right? Only the last column, either the third element or sixth element is 1, right? The third element is 1 actually. For the second row, we have first, second, fourth, fifth element as 1, right? For the first column, the second element is 1, so I can put 1. For the second column, again the second element is 1, so I can put a 1. For the third column, the first element is 1, so again I put a 1. For the fourth column, the second element is 1. For the fifth column, again the second element is 1. And for the last column, again the first element is 1, right? So you get all ones in the second row, right? For the third row, the last element has to be 1, and the last element is not 1 in any of the columns, so we'll get all zeros. For the fourth row, the second, fourth, and fifth element has to be 1, right? So basically, I can look at along the columns and basically complete my R square. Once we have done R square, we have to do R cube, R4, R5, and so on. And we need to see whether it is vanishes or it does not vanish. If it vanishes, that means the graph is acyclic, right? If it is non-vanishing, then we will see that the powers of R will start to repeat itself. And when that happens, then we know there is cyclical net, right? And once that is happening, we can compute R star and then take an intersection with R star transpose, and then I should get squares of 1 hopefully. If not, we have to permute and find the square of 1, that as we have shown earlier, and that gives me the information regarding the loops, right? So step 1, we compute R square, R cube, R4, and so on. I have just shown a few steps of how to do the computation, right? And then we will see whether it is vanishing or not. If it does, it's acyclic. If it doesn't, then it can be cyclic, and it is cyclic. And then we compute R star. We see when the R starts to repeat, and then we stop. And then R star intersection R star transpose is my something that gives me the information regarding cyclical nets. Okay, there can be few variations to this problem. Instead of R, you may be given R square, right? Now you cannot draw the graph for this problem. In the previous case, at least I could draw a graph. It was not required in the problem, but I could do the graph. But now I cannot do the graph, right? But still the same idea applies. I can compute R is 4, that is R square dot R square, R6, R8, and so on. And if it vanishes, then it is cyclic. If it doesn't, then it is cyclic, and it is simple to obtain by doing that, right? So you have to keep on taking powers until either it vanishes or it starts repeating. If it start repeating, it is cyclic. If it is non-repeating and vanishing, then we have acyclic graph, right? So we have acyclic r to the power n plus m vanishes for m greater than equal to 1, and if it is cyclic, then r to the power n will repeat, right? And repeat with some alternating powers, let's say every 2 power, every 3 power, depending on the order of the cyclical net, right? So with that, I want to stop here. In the next class, we will take some more examples and we will see how we can use graph theory for decomposition of linear system, and where it applies to for chemical engineers is to basically figure out which equations are basically simultaneous in the flow sheet, which balance equations are simultaneous, which are not, and then we will see like how we can apply to particular problems in chemical engineering. So with that, I stop here. Thank you so much.